So welcome everyone once again back to the Schönfeld Hörsaal, and we are opening a new chapter in our inaugural university-wide lectures. It's for this new academic year in 2023-24, and this one today is the very first one of our sequence in this academic year. So as you know, we are selecting newly appointed colleagues of ours who stand out for their excellence, for their interdisciplinarity, and for representing the Dresden spirit in the sense that they bring together the community of institutions available on the Dresden Concept, Science and Innovation campus. And our guest of honor today, Professor Yana Vaynzof, is, I would say, a prototypical example of all three of these things that I just mentioned. And so it's a particular pleasure to have her here today to give her university-wide inaugural lecture today. And as you know, TU Dresden has been, as one of its visions, to provide innovative solutions to the pressing challenges of nowadays. And one of the most pressing challenges, I hope we all agree, is the climate crisis. Of course, we have many other crises around the world, but if we do not make contributions to solve the climate crisis, no other crisis will be there soon. So we want to make a contribution, and the ecological sustainability for human life on this planet is an important goal for us to make a contribution. It has been taking center stage for us here at TUD in our research, and we will just hear one important example of that today. But it also more and more has been infiltrating, I should say, our teaching, our curricula. We'd like to make it possible for students of all subjects to refer to and learn about ecological sustainability, whatever their final degree will be. And I do know that our Vice Rector for Education, who is with us today, makes this a top priority for himself. So we have, in this line of thinking and strategy, our Faculty of Electrical Engineering and Computer Engineering has created a new professorship, a new chair for emerging electronic technologies. And it is exactly in this spirit of ecological sustainability that this was done, and we will hear from the Dean of this faculty just in a little while. And so we are extremely pleased that Professor Yana Vaynzof has been selected by the selection committee to fill this very first chair for emerging electronic technologies. And not only that, but she also, together with the professorship, has become director of the Institute for Emerging Electronic Technologies at the Leibniz Institute for Solid State and Material Research here at Dresden. And it's my great pleasure and honor to welcome its director, our colleague Professor Büchner, who will also give us a little speech just after mine. So this is the academic side of our very fine event today, but you know, we are a Universitas, we are a family-friendly university, and so we hope that we have welcomed the Vaynzof family quite a while ago, and it will continue to be so. And so it's my great pleasure to welcome Jana's husband today in the audience, as well as Mia and Emma. So welcome, it's so great to have you here. And so Dr. Fabian Paulus, I should give the husband a name because we are all about dual career. You're, of course, an academic individual in your own right. And so Dr. Fabian Paulus and Mia and Emma, and hopefully some relatives and other friends can watch online or later on our YouTube channel, because I'm also welcoming the attendees that follow the event online. So we are going to hear about how we can develop photovoltaic technologies that are not only high performance but also sustainable. And that is one of the crucial questions that Yana Vaynzof has been working on and will continue to be working on. And she will today in particular focus on semiconducting materials and their potential for sustainable large area applications. So that should be very exciting to hear. So this is a forward-looking field of research that will inspire research on the Dresden Concept Science and Innovation Campus, as well as its industry partners. That's what we hope. And it is also of quite central importance for TUD's continued strive for excellence and for its strive to compete in the excellence competition. So Yana Vaynzof's bio and CV will be detailed later. I'm not going into detail just now. I would just like to mention that we are extremely lucky and honored that we succeeded to attract in you, Yana, a professor of exceptional international experience and visibility, and just to say your research, your vision, and your intellect has gained you many awards, and rightfully so. And so we are very, very happy to have you here and that you made the decision to be with us and stay with us. And we hope this continues to be the case. So, but not only that, Yana Vaynzof also is highly committed to promoting equality and diversity in the STEM subjects. And we all do know as a University of Technology that this is very much needed. And so you may remember, some of you who have been following us loyally, that last year we welcomed another internationally renowned female professor to the Faculty of Electrical and Computer Engineering, our colleague Elisabeth von Haufe. And so we are very happy to now have another outstanding role model in the STEM field for young and aspiring doctoral students, master students, and postdoctoral students in engineering sciences. So on behalf of the TU Dresden community, I'm extremely pleased to welcome you. So a warm welcome again to you in this new role, together with your family. And let's just give Yana and her family a round of applause. So next, I will be speaking, as I mentioned before, the Dean of the Faculty of Electrical and Computer Engineering. It's our colleague Karl-Heinz Bock, who was just reconfirmed as Dean of the very same faculty. And after him, it will be Professor Bernd Büchner, the Scientific Director of the Leibniz Institute of Solid State and Material Research. I'm also welcoming its Administrative Director. Where has she been sitting down? Frau Schmidt. It's great that you're here as well. Welcome. And I'd like, before I leave the stage, thank all the organizers, because this event takes a lot of effort to coordinate, and it's between the faculty and the Leibniz Institute and the central administration. So it's our Chief of Protocol, Christine Milkau. It's Jörg Tanzmann, of course, of the Faculty of Electrical and Computer Engineering, but also from the Leibniz Institute, Dr. Carola Lange, who has been very helpful in supporting this event to come together. And the communication office is supporting us back there for Selbig, and then behind the screens there, our colleagues in the streaming domain helping us to bring it online now and later on. And don't forget, don't leave too soon. There will be a reception afterwards to toast with our new professor and to get into a nice chat across disciplinary boundaries. We very much hope so. So thank you very much for being here, and I look forward to the Dean's and Director Büchner's remark.
So thank you very much for the introduction. Dear colleague Professor Vaynzof, magnificent spectacularities, dear colleagues, dear students, dear guests, I'm very pleased that on the occasion of your inauguration lecture today, I can contribute to your laudatio. The appointment of our colleague Professor Vaynzof marked the first joint appointment between IFW Dresden and the Faculty of Electrical and Computer Engineering. We are very pleased that with an attractive offer, it was possible to keep Professor Vaynzof here at TU Dresden. This is a huge benefit for our faculty. So, as her research on nanomaterials for electronic components already had a strong impact on the faculty before her appointment, a visible sign of this is that she has been a member of the 3-person board of the CFAED, the Center for Advancing Electronics in Dresden, since 2021, and she already plays a significant role as the leader in the design of a new cluster of excellence. So you may imagine that these are very important roles, and then there was a call to the outside, and so we are happy you are here. So now you will hear much more about her very impressive career afterwards, but we know her from 2019 to 2022 on. She was appointed as a W2 professor for novel electronic technologies at our Faculty of Physics at the TU Dresden. Then, since January 1, 23, she was appointed a W3 professor for novel electronic technologies at our Faculty of Electrical and Computer Engineering, TU Dresden, and as a director of the Leibniz Institute for Solid State and Materials Research in Dresden. In our faculty, she now heads the chair for emerging electronic technologies. Mrs. Vaynzof, our new colleague, represents a research field that is as well synergistically integrated in our faculty, and with her research work, particularly in the area of nanomaterials for electronic components, she is also directly involved in the further development of information technologies and microelectronics at our faculty. Through your cooperation, Professor Vaynzof, or through our cooperation, Professor Vaynzof and the IFW is also anchored in 3 of 5 of our research profile lines at TU Dresden. So the joint appointment is therefore of a very significant importance for our faculty. The IFW Dresden has gained so then an outstanding scientist and networker as a director. This also applies to our faculty. We are pleased to have gained an internationally visible scientist in Mrs. Professor Vaynzof, who in addition to many advantages can be an excellent, also positive role model for young people in our technology and science environment, and in particular for women in engineering too. I know you are more a physicist and chemist, but we are glad you are in engineering too, so thank you so much. And we need it. As we all know, we need young engineers and young women engineers. For the faculty, the joint appointment of Mrs. Vaynzof opens up the opportunity for the first time to establish a long-term collaboration with the IFW. In research and teaching. And Mrs. Vaynzof herself naturally plays a key role in bringing this new connection between the faculty and the IFW to life. We warmly welcome you, wish you the very best of luck and success, and are happy to provide you support. We are also renewing this offer of collaboration and joint activities to all IFW employees to use our immediate neighborhood on the campus. The faculty is also open to more joint initiatives and would like to thank you for the many successful contacts and collaborations. So far and until today, this is already a well-working collaboration, but we will go for more integration and more collaboration. With the material research for electronic components and systems, there is a very large field of common scientific interests that can be worked on together. And actually, it is so large, the field, that we strongly need to work together to explore it. We are therefore very pleased that we were able to welcome Mrs. Vaynzof, an outstanding colleague, to our faculty, and that we are able to respectfully underline this again today as part of her inaugural lecture. Thank you very much for being here.
Dear guests, dear Yana, I have now the great pleasure to introduce the scientific vita of an outstanding, internationally very visible scientist, who is now director of one of our 5 IFW institutes. As you all will learn in the next minutes, Yana Vaynzof's scientific vita reads like an impressive list of honors and awards obtained at internationally leading places all over the world. It started with awards for her graduation thesis at Technion, the Israel Institute for Technology in Haifa, where she studied electrical engineering and obtained a bachelor back in 2006. Afterwards, Yana Vaynzof received the prestigious Gordon View Scholarship and completed a Master of Science in Electrical Engineering at Princeton University in 2008. For her PhD, she then moved to the Cavendish Laboratory in Cambridge University in the UK, again with a prestigious fellowship, the Henry Kressler Fellowship, awarded to her for extraordinary performance. After finishing her PhD in physics, in 2011, she was postdoc at the University of Cambridge, where she was the leader of the applied surface science activity at the Cavendish Laboratory and managed the photoemission spectroscopy research faculty. In 2014, Yana Vaynzof accepted an offer for a junior professorship at the University in Heidelberg. From 2014 to 2018, she was junior professor for physikalische Prinzipien der organischen Elektronik there. And during this time, she developed a new technique that allows mapping of the energy levels, landscapes, in various nano-optoelectronic devices. In this context, Yana Vaynzof was awarded an ERC starting grant in 2016. Moreover, as recognition of her academic achievements, Yana Vaynzof was awarded the Walter Kalkow Rose Gedächtnispreis in 2008, and later that year, she was selected as the winner for the Fulbright Cordwell Award. In 2019, Yana Vaynzof was appointed as a W2 professor at the physics department of TU Dresden. She has established a strong research profile in the area of emerging photovoltaics. For her contributions to the field of energy materials, she was awarded the Energy and Environmental Science Lectureship in 2020, and 1 year later, she was selected as Fellow of the Royal Society of Chemistry. Since January 1st this year, Yana Vaynzof has been appointed on a W3 professorship at the Faculty of Electrical and Computer Engineering at the TU Dresden, combined with the director's position at the IFW, the Leibniz Institute for Solid State and Materials Research here in Dresden. Again, this step was accompanied by grants and awards. She was awarded by an ERC Consolidator grant, was successful in the Leibniz Women Professorship Program, and raised a large EU project. The joint appointment of Yana Vaynzof by TU Dresden and IFW provides a great strategic added value for both institutions and for the science location in Dresden in general. As already mentioned by the Dean of the faculty, for the first time there is now a cooperation in research and teaching between IFW and the Faculty of Electrical and Computer Engineering at the TU Dresden. Professor Vaynzof's materials orientation and her competence spectrum from physical fundamentals to the design and integration of components are excellently suited to strategically shape this cooperation. The cooperation with the Faculty of Physics at TU Dresden is further enhanced. Among other things, Professor Vaynzof continues to operate her laboratories in the Kronebau as joint IFW TU Dresden laboratories. So there is no bridge between these neighboring buildings for the first time. And this will change at the point when the new building, which is again is a joint building between IFW and TU Dresden, will be ready in 2029. And then Yana will move in there with their activities. Yana Vaynzof also introduces a new impact to IFW's research program, the 2023 newly established research area Sustainable Materials and Technology in the IFW research program will receive a significant directional impetus and a substantial strengthening. Professor Vaynzof's research focused on physical and chemical phenomena in solids of interest to sustainable energy applications, which fits perfectly with IFW's general mission as a Leibniz Institute and, in particular, with IFW's specific research program. She deals with a broad spectrum of materials ranging from inorganic quantum dots to hybrid perovskites and inorganic semiconductors, and offers numerous starting points for joint projects within the IFW and other Leibniz institutes. Finally, Professor Vaynzof's expertise in developing advanced spectroscopy methods for materials characterization strongly complements and strengthens the strategic development of methodological capabilities at IFW. Also, many research groups in the Dresden network will benefit from this expertise, thus strengthening the regional cooperation across various institutes. At this point, I would like to take the freedom, ending this short laudatio with a few words regarding my own experience with Yana during the last months. So Yana has been at IFW for 10 months only. I've never experienced a person who has left such a big footprint in our institute in such a short time. This concerns changes in the research program initiated by Yana. Her great success in third-party funding and collaborations is, for example, for the first time, we now have a joint project with IPF, and that again was initiated and written by Yana mainly, let's call it like that. In particular, this footprint also concerns her great influence on ongoing discussions on IFW's future and our further strategic development. For me, this is really more than impressive. And therefore, I'm absolutely sure that Yana has the ability shaping the future of our institute in many ways. This concerns topics and visibility of IFW's research, initiating and strengthening cooperation in Dresden and beyond, as well as improving our outside appearance as a world-open, diverse institute. Yana, I'm really happy that you decided to come to us to be director of our institute. I hope that you stay at least for a couple of decades. And now I'm looking forward to your presentation.
So, first of all, I would like to welcome everybody and thank you, of course, for the very nice introductions. And before we start, I want to tell you, all of you will need to use your phone during the presentation, so you can already get it out and get it ready. And by the end of the talk, all of you will have some perovskites on your phone. I didn't say in your phone, but on your phone. So let us start. It's really a pleasure for me to show you a little bit of what we do in the lab. And we work with materials which I believe are truly magical. But the real magicians are my students, some of whom I'm very happy to also see here in the audience. These are the real magicians who work in the lab and do true magic. Of course, we don't work alone. We also have many international collaborators. I show a few of them here. And it would not be possible to do any of our work without very generous funding, both from local agencies, of EU agencies, German agencies, and even Fulbright Commission from the US. So thank you for making it possible for us together to work on a very important topic. And the topic that motivates all of us together is the issue of global energy demand and how we can actually produce enough energy. So the topic of affordable and clean energy has been designated as the 7th sustainability goal by the United Nations, which is claiming that energy is central to nearly every major challenge and opportunity that the world faces today. I cannot agree with this statement anymore. Now, if you follow the global energy demand over the last couple of centuries, we see clearly that starting from the 1950s, we have an enormous rise, and it's projected to continuously increase by 1 or 2% every year. So we clearly are able to satisfy the energy demands at the moment. So you might ask yourself, well, what is the problem? And I would claim that there are three major issues that need to be addressed. The first one is air pollution. Air pollution, for which energy generation and energy production is largely responsible, is at the moment estimated to kill approximately 7 million people per year. So we really have to do something there. Another issue is the issue of safety, accidents. We have many energy-related accidents, not only as the one depicted here, but also related to mining of resources that are used for energy production, their transportation, building of power stations, their maintenance, and so on. And there are many examples for such accidents. And the final issue is perhaps the most pressing, also as highlighted by our rector, is that energy production comes with enormous greenhouse gas emissions. And we really have to do something about it if we want to have a planet to live on. So let us quickly compare what are the different energy sources in terms of safety and also in terms of cleanliness with regards to greenhouse gas emissions. And you can see here a very interesting trend, which is the safest sources are also the cleanest. In particular, we see that solar is by far the safest and almost the cleanest. What really motivates me about solar energy is that the amount of sunlight and energy that hits the Earth in just an hour and a half is enough to supply our entire energy demand for a year. So by the time we'll finish this talk and maybe a Q&A and go to a nice get-together afterwards, that would have already been enough energy for the full year. So there are many ways to use the solar energy for energy generation, and one of these ways is photovoltaics. Photovoltaics enables a direct conversion of sunlight into electricity. That obviously doesn't satisfy all of our energy demand because electricity consumption is only approximately a fifth of the total energy needs, but we are able to supply the entire electricity required by the world if we were able to cover the planet, 0.3% of the planet, by solar panels, which of course is arguable how much it is, but it's actually not very much of the total land that is available. Now, if we look at the existing technologies in terms of photovoltaics, by far most of them are made from silicon. Now, this is wonderful, and I hope all of you have silicon solar cells on your roofs, and hopefully in TUD as well. We will have many more. But let us quickly have a look how we get there, how we get the solar panels. So we actually start with silica, which is essentially sand. Now, from sand, you can't really make solar cells, so you have to do a couple of things. And the first thing you do is you expose the sand to very, very high temperature in order to create a crude silicon product. Now, from that, you expose it once more to a high temperature and a chemical process to actually form polycrystalline silicon. That is still not enough. We have to expose it once more to a very high temperature in order to melt it, and by melting it, to form a single crystalline silicon ingot. You can't make a solar cell directly from the ingot. You have to do a couple of things extra. So first of all, again, at a high temperature, you have to shape the ingot into the right shape. You then have to do a number of additional processes ranging from doping, texturing, chemical processing, at the end contacting, until you finally get your silicon solar cell. But one silicon solar cell is not going to help us. We actually need a module. So there is yet another step, at this time somewhat lower temperature, that includes soldering and lamination, and finally we are able to achieve our silicon module. And you can see that the energy investment into making one solar cell is really rather high. So before we can generate any energy, we have to first recuperate the energy that we invested. And you might ask yourself, how come we need to do all of that? Why can't we just take, perhaps the crude silicon or the polysilicon and just use that? And the reason is because of the structure of silicon in a crystal. So let's look at it. We imagine a crystal as an sort of order structure of atoms, as I depict here, right? It's very easy to do in PowerPoint. And because it's a semiconductor, you have some bands that are affiliated with it. So a valence band, which is the filled band, and a conduction band, which is the empty band. And while we visualize our crystal like this, we then imagine that we shine light onto our crystal, and that generates enough energy to promote an electron from the filled band to the empty band, leaving a hole behind, and now these electron holes are available to be collected for electricity. So this is all very nice, but the reality is quite a bit different. In reality, crystals have defects. So in the case of an inorganic crystal, for example, you could have a vacancy, an absence of an atom where it should be. That would result in a formation of a so-called gap state. So basically an additional state in the middle of the gap where states really should not be an ideal case. Now you have other types of defects, interstitials, where you have an extra atom where it shouldn't be some more states. You can have impurities, you can have substitutions, and finally you can have grain boundaries. Even in clean crystalline domains, when they interface, you might have additional states. All of these result in a simple thing. Instead of being able to collect the charges, actually these are states where charges can then recombine. So there's a loss mechanism. A material like that, an inorganic crystal like that, would be then termed defect intolerant. And that is the reason why we need these very high temperatures to purify the crystal as much as possible, to get as close as possible to the structure where no subband gap states are formed. That's why we need single crystalline silicon solar cells. Now, if we look at the performance of silicon solar cells, and in this case, I will follow the power conversion efficiency, which is the portion of energy from the sunlight that we can convert into electricity, you can see that it took a number of decades to reach the current record of 26.1% for crystalline silicon. So of course, there were many different processes that were optimized with time, and it's 50 years or so, and now we are in a good shape. On the other hand, there is a new player in town. There is a new technology that is coming into play, and that is the perovskites. In just a decade, it was possible to demonstrate comparable efficiencies to silicon, and that I find absolutely remarkable, with a rise that is not compared to any other technology. So now this is the time for you to take out your phones, because we need to discover together what is a perovskite. So please have a look. You can scan this QR code, and once you do, you will have a little perovskite crystal structure on your phone, and you are able to rotate it, and you're able to make it bigger and smaller. Now in the left corner, you will see a little sign with the letters AR, augmented reality. So I would ask you to now press on this so you can put the perovskite right here in our augmented reality. If you want, you can put it on my hand or on the desk. While you do that, I would really like to thank Professor Günther Thiele from TU Berlin, who actually created the augmented reality crystal database. So I hope you all have it. Yes? Okay, I see everybody's doing augmented reality. Fantastic. So if you see it, and if you don't have a phone, you can see it here, you should be able to see a crystal that looks like this. Let me see a show of hands. Who can see the crystal on their phone? Okay, quite a few. Fantastic. So let's go through the structure together, because as you can see, it's a little bit more complex than just silicon. So first of all, it's a ternary structure that follows the formula ABX3, as you can see here. So let's start sort of side by side. The teal ions that you can see positioned in the center are the so-called A cation. So these could be small organic molecules, like methylammonium or formamidinium, but also could be an inorganic ion like cesium. In the B side, the black in the corners is either lead or tin, another cation. And finally, these black ions are surrounded all around in octahedra of halides. So halides could be iodine, bromide, or chlorine in magenta. And the important point is that it is a corner-sharing octahedral structure. So you can see that the corners of each octahedra, I guess you can see it here, are meeting together. Okay, everybody has it? Now's the time to take a picture so that you can have it on your phone. Okay, and the interesting thing about perovskites is that we now can examine exactly what happens when we introduce defects into them. So again, we have a crystal structure, and we imagine that we shine light, and we generate charges which we can collect. What happens when we introduce defects? For example, a vacancy. In this case, a vacancy results only in a very shallow defect, not as deep as we had before. Alternatively, we could have an interstitial, which normally we would expect to lead to a deep defect in the middle of the gap. But the crystal lattice of the perovskite is very soft and is able to actually change a little bit its configuration such that that defect is not formed. Other types of defects can actually lead to states in the bands and thus not affecting at all the electronic structure. Same happens with grain boundaries, which lead only to formation of very shallow defects. And that means that in this case, the solar cell would not really lose much performance because of the presence of defects. Such material is then termed defect tolerant, and that there's no need for high temperature processing. In fact, you can process it in a very, very simple fashion, and you don't need a single crystalline perovskite solar cell. So one of the most important properties for a solar cell is, of course, to absorb light, right? That's why we say black magic in a bottle. So let's look a little bit at absorption of semiconductors and how it looks like in a very simplistic way. Now, again, if you have bands, you have your valence band and conduction band, and you want to absorb light. If you shine light at an energy which is not sufficient to promote an electron across the gap, you would actually have zero absorption coefficient. Now, in case you shine light with an energy sufficient to promote an electron all the way to the conduction band, you will have an onset for your absorption. Now, of course, if you shine light with even larger energy, you would have sufficient energy to absorb the electron promoted to the conduction band, and so you would have an absorption. So in a very simplistic way, there will be no absorption below the gap and absorption above the gap with a sharp interface. Now again, reality is of course not as easy and as sharp as I show it in PowerPoint. So in reality, what happens is that the bands have a degree of disorder in them, energetic disorder, which means additional states are sort of leaking into the gap. And the result of that is that the onset for the absorption is not as sharp as I show it here, but rather is actually a little bit more sloped. And depending on how good the semiconductor is, it will be, more and more leaning. Now, that means that the sharpness of our absorption edge is actually representative of the degree of energetic disorder within our material. So what happens in the case of perovskites? If we compare the absorption edge of perovskite, in this case it's a methylammonium lead triiodide perovskite shown here in red, it is essentially as good as gallium arsenide. Those of you who work with gallium arsenide know it also requires very, very high temperatures. In fact, it is even better than that of silicon. So energetic disorder within these perovskite semiconductors is remarkably low. And you will see later how they're made, and you will be amazed that it's even possible. Another important point is to look at the actual intensity of this absorption coefficient, how high it is. And you can see that the absorption coefficient in perovskites is significantly higher than that of silicon. Of course, the physicists and engineers in the room know exactly why, but the outcome of that is that while silicon solar cell will typically be, a couple of 100 microns, so it's essentially as thick as maybe a postcard, a perovskite solar cell can be a factor of 1,000 thinner because it absorbs light so well. Now, we see here an example for a perovskite, but of course you saw we can have many different combinations of elements that we could put together. While in the case of silicon or even gallium arsenide, we have one band gap, one material. Here, we can tune the band gap. we can simply change the composition, for example, ranging from cesium lead chloride all the way in the blue range with very large band gap, and then gradually changing the halide to bromide and then to iodine across the visible range, and then finally going to mixed tin lead systems, which are going all the way into the near IR. And that means that with a single material, purely by changing its composition, we are able to tune the band gap from 1.2 electron volt to 3.1 electron volt. And that, of course, opens many possibilities, not only for photovoltaics, but also for other applications. Now, I mentioned to you that silicon is a single crystalline material. So if we look at the microstructure, if we really visualize it here by electron microscopy, I like this example because it shows an interface between a single crystalline silicon to a polycrystalline silicon. And you can clearly see in the case of the single crystalline silicon, there are no grains, there are no boundaries, it's just perfect. Now, how would perovskite look like? We actually examined a number of ways to control their microstructure, but in all cases, you can clearly see this is a polycrystalline material. We can tune the grain size from tens of nanometers, maybe to a few microns, but still many interfaces, many boundaries, and yet they work remarkably well. You can also see here the thickness that I just mentioned to you. So in this case, you can see in the cross sections that the thickness of the perovskite layer would be perhaps a couple of hundreds of nanometers. And that's much, much less than the hundreds of microns we would require for a silicon solar cell. So finally, how do we make them? So I can tell you, all of you can make them. You can come to my lab, it's very easy. You don't need to be a physicist or a chemist or engineer. Everybody can make a perovskite. Because what you need to do is you need to mix a few powders. So the key one I would say is lead iodide, is the yellow powder here. It's the main precursor for lead, although others are also possible. And the other precursors are normally colorless powders. Now you would just weigh them on a balance and then mix them in a vial. All you need to do now is you need to take a solvent and add it, and you will get a pale yellow solution that is ready for film formation. Now, how would we form the film? Typically, in the case of solution processing, especially in the lab, we would use a process called spin coating. So how is it done? We take a small amount of this pale yellow liquid, we deposit it on a film, on the substrate that then begins to rotate really, really rapidly, and that makes it possible to form a homogeneous layer. Now, the key in this process, and this is the process that is used most commonly, is at some point during this rotation, you need to apply a so-called anti-solvent. So a solvent that would be able to withdraw the whole solvent from the wet film and thus trigger the crystallization. And typically you can visualize it because the film turns from essentially transparent, because it's so pale yellow, it looks transparent, into brownish color. And we then complete the crystallization by annealing the film. So let me show you how it would work. So here a film is spinning, you can see it's transparent. And then you can see that the scientist is adding the anti-solvent, and now you can see it's slightly brown. But the magic truly happens when you anneal it at relatively low temperature of perhaps 100 degrees. And you can see the film turns essentially completely black. Even though it's thin, it absorbs almost all the light. So it is very clear that this step of the anti-solvent is quite crucial, because that's the trigger for the crystallization. And looking at literature, we saw that there is many scientists looking at different anti-solvents, and it wasn't particularly clear, is there a best anti-solvent? What are the processes involved? And so we decided to look at a series of different anti-solvents with a variety of properties. I mean, the chemists in the room are happy. There are some chemicals on the screen. So we looked at these anti-solvents and we realized something quite remarkable. It seemed like all the anti-solvents fall into three categories. In type 1 anti-solvents, if you deposit them quickly, you get very good devices. If you deposit them slowly, even though it's the same anti-solvent, you either don't get any performance or you get rather poor devices. Then there is a second category of anti-solvents where it doesn't seem to matter too much if you do it slowly or rapidly. And finally, there is a third category where you have to work slowly. If you deposit them slowly, everything works, you get high efficiencies. If you do it too fast, you have poor devices, or in the case of, you see anti-solvent 14, that's mesitline, no devices at all. And so the first conclusion, which really surprised us, is that essentially it's possible to make a high efficiency device from any anti-solvent, so long as you know how fast or slow you have to apply it. And the reason for that, and the reason for the categorization of the different solvents into the 3 types, is related to the ability of the anti-solvent to dissolve some of the precursors, in which case, if you can dissolve them, you have to work really fast, because otherwise you're going to withdraw them from the film and the crystal won't form correctly. The second key property is how well the anti-solvent mixes with the solvent, their miscibility, because you want to be able to withdraw the whole solvent very rapidly and effectively to really trigger the crystallization. So now that we realized how anti-solvents work and how to apply them in the optimal condition, we are able to use them to actually passivate even some of these shallow defects that I showed you that are formed. So the way we did it is we incorporate organic halides in 2 ways. First of all, we wanted to put them below the perovskite layer to pacify the buried interface. And secondly, we wanted to put them above, like a sandwich. So to incorporate them below, we take them and create a pre-wash step. So essentially, we put some of them onto the substrate before we start forming the perovskite layer. To put them above the film, we actually don't need an additional step, because we anyway have to apply the anti-solvent, so we can simply put these passivating agents directly into the anti-solvent and form the layer. Now, once we did that with this dual passivation strategy, both at the bottom and at the top, we were able to improve all the photovoltaic performance parameters, reaching an efficiency of 23.7 for a device that is entirely solution processed and at low temperatures of only 100 degrees. Now, while working with solvents is remarkable and interesting, it also opens opportunities for things like printing. There is another way to process perovskites, and that is by thermal evaporation. In this case, again, you take the same precursor powders that you would use for solution processing, but you would just deposit them thermally in an evaporator. Now, the advantage here is that, first of all, it's solvent-free. You don't have to worry about the solvents at all, and also you can form the perovskite even at room temperature. You no longer need to apply any type of heating. Evaporation is also particularly promising because it's industry relevant. There are many technologies that already are based on evaporation. For example, organic solar cells or organic LEDs. So in my group, one of the first studies we did is to be able to control the crystallization. In the case of solution processing, this is done by the choice of solvent and anti-solvent. Here, we had to come up with a different strategy. Now, we worked on an inorganic perovskite. This is cesium lead triiodide. And when you just evaporate that on its own, you can see on your left-hand side, the microstructure doesn't look good. There's lots of grains, lots of defects. It's really not great. And the orientations of the grains are all different, as you can see in the X-ray diffractogram on top. The efficiency of such devices was really disappointing, only about 3%. Then we added a small amount of additive that we co-evaporate along the perovskite precursors, called PAI. In this case, you can clearly see the effect on microstructure. You have a columnar growth where the grains grow in a very ordered fashion. And you can also see it in the X-ray diffractogram, because you see that there is a single crystalline orientation. So all the grains grow in the same way. And the performance significantly increased to 15%. For an inorganic perovskite, this is already very promising. And of course, again, the advantage is that you can very easily scale up the thermal evaporated films to mini modules and even modules. Another great advantage of vapor deposition is related to semi-transparent solar cells. So in this case, if you were trying to make a semi-transparent solar cell, you actually don't want to absorb all the light. So you want to make the film very, very thin in order to absorb just a little bit of the light. If you were to try and do it by solution processing, something like this happens. You can't form a compact layer because the way the crystallites grow, you actually have a lot of gaps between them. And so you can't really use that for a solar cell. On the other hand, if you do it by thermal evaporation, you can see that even a 10 nanometer thick film, which is very, very thin, forms a completely compact pinhole-free, homogeneous, and uniform layer. Now, when we look at these films, Of course, at the end, the idea is that they are semi-transparent, so we have to examine their transparency. That is identified by the average visible transmission, or so-called AVT. You can see that the 10 nanometer film is a little bit beige, but you can easily read a newspaper through this type of layer, right, with the average visible transmission of 74%. When incorporated in solar cells, such thin layers reach efficiency of 3.6%. Again, these are incredibly thin. And in fact, we believe that this is the thinnest perovskite solar cell ever fabricated. Now, the combination of techniques and also some additional properties of perovskites I will show you in a minute also make it possible for us to investigate completely new device structures that don't exist yet for photovoltaics. So if we look more broadly across the field, we see that the concept of heterojunction is very popular in different technologies. And the reason for that is we want to interface materials with different electronic structure or different electronic landscape in order to guide the charges to be generated and pass them to the contacts. Now, in the case of, for example, organic solar cells, and we had a great talk by Elizabeth about that, we have to interface two types of organic materials, each with different optical and electronic properties, the so-called donor-acceptor heterojunction. In the case of silicon, I briefly mentioned, you have to dope either side of the junction in order to control the electronic structure, either N-type or P-type. Dimensional heterojunctures are those where you interface a 3D and a 2D component. This is very typical for both perovskite solar cells, but also SIGS technologies. And we considered, why not think of a new type of concept for heterojunction? And we propose a phase heterojunction. So what is a phase? I showed to you a perovskite crystal structure, but this is only one crystallographic phase, one particular arrangement of the atoms that leads to a certain set of properties. But many materials, many semiconductors exhibit the so-called polymorphism, which means compositionally identical components can exist in different crystalline configurations depending on the arrangement of atoms. And so we thought, why don't we interface the same material, so compositionally identical, but crystallographically different? And by using that, we will form a phase heterojunction. And perovskites are perfect for demonstrating this new concept. So here I show you an example with cesium lead iodide, again an inorganic perovskite, that exhibits clear polymorphism. It exists in 4 different phases. The alpha phase resembles that you saw on your phone with the cubic structure. Now, with the beta phase and the gamma phase, you see that the lead octahedra become more and more distorted. And finally, in the case of the delta phase, you can see a completely different structure. So the octahedra are no longer corner sharing, they are now phase sharing. And that means that that is the sort of outlier. You can also see that 3 of them, the alpha, beta, and gamma, are black, and so interesting for photovoltaics, while the delta one is yellow. It has a very large band gap, and it's really not very interesting. So we wanted to use 2 out of these 3 black phases to create the structure. And the way we did it is by combining the 2 methods for forming a perovskite. The bottom layer, the beta cesium lead iodide, was formed by spin coating, by solution processing. Now, once it was formed, we were not able to deposit the next layer by solution processing because we would have dissolved the first layer. So here we used thermal evaporation to deposit cesium lead iodide in the gamma phase. And you can clearly see here in this cross-sectional electron microscopy image that you see distinct 2 layers of the material, the underneath one in the beta phase and the top one in the gamma phase. Now, once integrated into devices, we observe something remarkable. The single-phase devices, you can see here in red the beta phase, and in purple, dark purple, the gamma phase on its own. Single-phase devices reach at most about 15% in power conversion efficiency. On the other hand, as we progressively made the phase heterojunction device thicker, by increasing the thickness of the gamma layer on top of the beta, we were able to reach a maximum efficiency at 100 nanometers of the gamma phase, surpassing the barrier of 20% for an all inorganic perovskite device. I would also highlight that this is a proof of concept, but since polymorphism exists in many different systems, it could be applied to other material systems as well. So everything I showed you right now, you would say, that's it, let's put perovskite solar cells on our roof, right? I mean, they're fantastic. I agree, but there's a couple of challenges we have to solve first. The first one is still related to scalability. So here you can see a study that compared the available information about lab-scale devices, also mini-modules, sub-modules. You can see we don't have any reports on small modules so far. And in comparison, you can see the silicon commercial module you could buy right now. So you can clearly see we need to work more about scalability, because as we increase the area of the device, the performance actually drops down. So we need to make sure we develop new processes so that that doesn't happen and continue to a larger scale. The next problem is the problem of stability. So in this case, the study compared the so-called T80. So basically, how many hours did it take until the device reached 80% of its initial performance? And you can see that the vast majority of papers published, in this case more than 6,000 reports, actually report just a couple of hundred hours of stability. Only one report was able to demonstrate 80,000 hours, which is approximately 9 years. But even this is far below the 25 years that silicon solar cells are offering us. So we have to solve the issue of scalability and stability before we can go to commercialization and the market. Another issue, which is not as often discussed, is the issue of reproducibility. And this is something we examine a lot in my lab. Here I will show you one of our studies where we compared different bottles of the same lead source, in this case, lead acetate trihydride. So we buy it from two suppliers. These are very famous chemical companies with the same purity and the same properties, but you can clearly see that they're not the same. Something is very different about these precursors, and we don't know what. So not only the maximum performance that you can reach with each bottle is different, but also the distribution of performance, even though you do the exact same thing, is very, very different. Now, some of these issues are related to the fact that, of course, all of these devices are done by my magicians, and they are human, so there might be some human errors, so there's a human factor to be involved. This really highlights the need for process automation. But other factors are completely unknown and have to be identified before we can really transfer it to mass production. Now, I showed you a lot about photovoltaics, but perovskites are very interesting also in many different applications beyond photovoltaics. Obviously, in optoelectronics, like I told you, we can tune their emission properties, we can tune their structure, and so light-emitting diodes, lasers, photodetectors, some of these applications, even those that do not directly involve light, like memory applications or used for catalysis. And the final range of applications is related to electronics. For example, field effect transistors. Could you make electronics based on perovskites? And, of course, another interesting technology is thermoelectrics. Now, for the latter two, there is a specific process that you need to develop for perovskites, which is doping. I will briefly remind you what is electrical doping. It's basically a process by which we can vary the charge density in our semiconductor. So one way to do it, for example, would be to use an N-dopant, so a molecular structure with energy levels that are designed such that when near our perovskite, an electron will be transferred from the N-dopant into the perovskite, and by doing so, we'll dope it N-type. Alternatively, you can have a p-dopant, where you have the opposite process with an electron passing to the dopant, leaving a hole behind. And by doing this, you can control how many holes do you have, how many electrons do you have. Now, to visualize what doping level there is in a material, it can be done by looking at the position of the Fermi level. So in a simplistic manner, when the Fermi level is close to the conduction band, it's an N-type material, so it's in the upper half of the band gap. And when the Fermi level is close to the valence band in the lower half of the band gap, it's p-doped. Now, if you think about perovskites, you could say, well, there's no problem. We'll just take our perovskite precursors, put some dopants in, right, mix them up, and then we'll have a doped perovskite, right? It should be very easy. Now, the problem is that, and a lot of these studies have been done, when you try to do it by solution processing, you have to involve the solvents. And in perovskites, the solvents mediate the crystallization of the perovskite crystal, and by doing so, expel the dopants out of them. And so that means that when we then anneal the sample to remove the solvent, we don't actually end up in the doped perovskite structure we wanted, but most often we end up in a segregated case where only the surfaces and interfaces are modified. An alternative to that would be to co-evaporate the dopants alongside the perovskite precursors all throughout the layer. And this is exactly what we did in our very recent study, where we selected a molecular N dopant and a molecular P dopant, and then we incorporated them into the perovskite by co-evaporation. And you can see here the position of the Fermi level with respect to the undoped reference that clearly shows that as we increase the evaporation rate of our dopant, so we put more and more dopant inside, we can tune the position of the Fermi level. In the blue range, that will be in the upper half of the gap, so we N-dope. In the green range, you can see it's in the lower half of the gap, so we P-dope. Now, the engineers among you will say, okay, you have N-doping, you have P-doping, you have to make a PN diode. Yes, we do. So we made a very simple proof of concept PN diode and an NP diode in a symmetric structure with gold contacts. And you can clearly see that there is rectification. Now, I will give you, these are not the best diodes, but it's also the first perovskite diodes. And PN diodes are really critical because these are the building blocks of electronics. So this is our starting point to really go into perovskite-based electronics. So to conclude, I hope I convinced you that metal halide perovskites are truly remarkable and magical. It's possible to process them at low temperatures, even at room temperature, by a variety of very simple methods. And I really welcome all of you to come to my lab and make some perovskites. Now, we can tune their optical properties, which is really wonderful for a semiconductor because it enhances the applications that are possible. We have fantastic performance in solar cells already, but it has a great potential also for other applications. We have a lot of work on the way because the challenges need to be addressed before it can be a product, but we will do it. So I would like to thank you for your attention, and I really look forward to your questions.
Thank you so much for your really outstanding and really very inspiring talk. So thank you so much. And we are very glad to open the discussion now. So are there questions to Professor Vaynzof? So just to actually bridge over, my question would actually be, when you showed on your very last slides that you have to overcome two challenges. And one challenge is the stability. So could you maybe go a little bit into detail which stability or degradation mechanisms you actually face? And maybe that would be interesting to me from the point of systems integration and reliability.
Yeah, so there are many different causes of instabilities in perovskite. Obviously, environmental causes are truly important. So exposure to oxygen or to humidity then causes degradation of the perovskite, typically back into the precursors. Another cause of instabilities is the fact that these are ionic semiconductors. You could see it's a very soft lattice. These are all ions. And once you start applying certain triggers to these ionic semiconductors, could be light or could be bias, the ions begin to move. And so one specific source of degradation is that the ions leave the perovskite and go into the extraction layers, into the contacts, and so you have some migration. And this can be, of course, mitigated by ion blocking layers that are not permeable to these ions.
Thank you very much. Now, in the meanwhile, are there further questions, please? Professor Ferdi?
Yeah, thanks, Yana, for this great talk. I mean, there should be more students in the audience. So I have maybe a bit specialized question, but I was very intrigued by what you showed, let's say, on the different phases that you can achieve by annealing at different temperature. And I was thinking, what happens now if you take, let's say, if you start with the yellow system and you put plasmonic particles inside, and you then illuminate them, which will cause a very local heating, yeah? Which can go very high in the temperature, but it's not. It's only happening in the very close vicinity of the particle. So could this be a way to create, let's say, phase gradients very locally, or is the system just not switching so easily?
So it will depend on the temperatures that are generated. So if you're trying to form, for example, an alpha phase cesium lead iodide, you're talking about 300 degrees.
No problem.
So, no problem. Okay, this could be interesting. The other thing to consider is how the ions from the perovskite would interact with the metal nanoparticles. In some metals, they would actually form then non-metallic phases. Maybe silver will convert to silver iodide. So one would have to examine that. But that could be interesting. We typically are aiming towards phase pure perovskites, but it could be interesting to play with that and look if we could form sort of gradients of phases within the perovskite.
Thank you.
Yana, thank you very much for a beautiful talk, and of course, as always, amazing science. I have a question. So in inorganic solar cells, there is this concept of tandem devices, which are kind of, very expensive, but also very good with very high efficiencies. And as you showed, since perovskites can be so tunable, can one go even above this 26% limit by kind of combining smartly the band gaps?
Absolutely. So there are a variety of tandems possible. Perovskite tandem is possible. Silicon perovskite organic. There's a whole range of tandems already demonstrated. I would say that perhaps the most promising technology is really silicon perovskite tandem. So it's already been demonstrated to achieve 32.5%, which is really remarkable. And it allows us to take advantage of all the infrastructure that is already available for silicon, and now just add a few more layers on top in the shape of a perovskite and actually push the efficiency much higher. So my prediction would be this will be the first product on the market.
Thank you very much.
Any further question? Here, please.
Thank you, Yana, for this brilliant talk. Congratulations once again from my side. And I already see there are some synergy effects for the future in terms of stability and scale-up. We can talk some other time. I have a question regarding the challenge the lead-free perovskites would pose to you.
Lead-free perovskites?
Yeah. What is
I was hoping somebody would ask me, right? Sustainability, what about the lead?
Yes,
so
that was my
let
question.
us start with a quick poll. So who thinks that lead-based perovskite solar cells have more lead than silicon-based solar cells? Now, I wouldn't be asking if you all know the answer. Silicon-based solar cells have 7 times more lead in them than perovskite-based solar cells. That would be quite surprising. So there is, of course, a lot of effort to replace lead by tin. And there are some promising results, but tin suffers from a clear disadvantage, and that is it is even less stable than lead, and typically is prone to oxidize. And so these devices, they work, but for a very short period of time. And there is so far no clear strategy how to stabilize it sufficiently. There is also some arguments to be made that certain studies comparing the toxicity of lead-based perovskites to tin-based perovskites show that there is not necessarily a huge advantage in going for tin. And finally, one way to think about it is that we know lead, and we have a lot of strategies to contain lead. So there is, lead sequestering materials. There is a whole range of strategies that we can make sure the lead stays in the solar cell and doesn't go to the environment. So, perhaps the enemy you know is better than the enemy you don't know.
Question here. Yeah.
Beautiful. I was really intrigued that you can tune the absorption spectrum. And as a basic question, could you build perovskite solar cells that only absorb the UV spectrum, and then that could be printed on glass windows, or that pass through the green and the blue light, but you're still harvesting energy, say, by converting only the red wavelengths?
So what you're talking about is essentially, again, semi-transparent solar cells, or in this case, I would say rather visible transparent solar cells, is absolutely possible. Of course, the efficiency will not be very high, because your band gap is really large, and so you're collecting really a small fraction of the sunlight. And that's why in my group, we more focus on the ultra-thin perovskite solar cells, where it can still absorb light, but they are relatively transparent. Perhaps they could be used more for shading. As we know, there will be more and more sun and more heat, so this would be an interesting approach. But you are right, of course, by tuning the composition, we can also create only purely UV-absorbing solar cells.
Are there more questions? There's one there. Yeah, please.
Yeah, thank you.
We can hear you.
Okay, just like that. So you mentioned the lack of reported modules based on perovskites. So in your view, what are the challenges to develop mini modules and modules, and what is the field overall doing about it?
Yeah, so this is a great question. I showed you the issues with reproducibility on the small scale, and you could see it was precursors, it was a range of other properties. We can have, if we look at the perovskite field as a whole, there's a perovskite database, which basically includes many hundreds of papers and thousands of devices. You can get everything from 0 to 26.1. And we need to identify exactly what happens already on the lab scale before we go to the large scale. Because then, what can happen is that you can have different areas of the module acting differently, and then the overall performance will be compromised. So in terms of what the field is doing about it, definitely development of new techniques. I will still say that perhaps 90% of researchers work on spin coating. This is not scalable. We can make perhaps a 5 by 5 centimeter square layer, no more. So more and more, I see that the field is going towards thermal evaporation, perhaps sputtering, other new techniques, also, of course, printing, slow dye coating, many different technologies to go to the large scale. And that means that we sort of have to learn everything from scratch, because all these processes are different than spin coating. And we are very good at spin coating. We can get 26.1%, but that doesn't work and doesn't translate immediately to the large scale. And that's what the focus is on now.
Thank you very much. There was a second question, another question here, please.
Yeah, the perovskites is one structure, and you and others discovered that this is good for this purpose. Now, can you imagine that there are other structures out there entirely different, which are perhaps even better? So is there, apart from the empirical insight that perovskites work well, are there more insights into a construction principle of what makes this fault tolerant or defect tolerant?
It's, I would say, more a question for theoreticians, perhaps something you would like to address. There's definitely a lot of effort going on to try and predict new structures and new materials and look into what their properties might be and how suitable they might be for photovoltaics. I would also like to mention that perovskites, even halide perovskites, are not new materials. They've been known for many years. They've just never been tested in a solar cell before. And that's why you could see from 10 years ago an incredible rise, but this rise could have been there 50 years ago if we only knew to test them. So I believe that there are other materials out there, perhaps even materials that are already available and you could make them, but we never actually examined them in a photovoltaic concept. But yes, perhaps you could predict some new structures for us. That would be wonderful.
There's a question.
Yeah, thank you. Thank you, Yana, for a great talk. I do know that you're very much interested not only in conserving energy, but also in thinking about the aftermath. So have you given some thought about the decomposition of the material?
So if you're asking about recycling?
I wanted to avoid that term because I learned that this is not the favorite term any longer. But yeah, so what do you do after it lost its functionality?
So it's possible, so there are two ways I will answer that. The first one is that it's possible to dissolve the perovskite layer out of the device and also the extraction layers, and in fact reuse the glass and the other layers for making the next device. In some cases, there are some reports that show that's even better. It leads to a better efficiency once you actually use recycled components. And the second answer is that we have an ongoing collaboration with an expert on recycling where we collect all the devices we make in our lab and we send it to them. The first challenge was that the recycler said you have to give us 0.5 kilo of solar cells. And it turns out that that's actually a lot of solar cells. So we are collecting them. We have a special case where we just collect the solar cells that we no longer need, and then they will develop new ways that are specifically targeting perovskite solar cells.
Is there any idea about the energy consumption for that process?
For the recycling? Well, not yet, although there are some studies looking at the life cycle analysis and also in terms of the recuperation time that one would require, and it's very competitive. It's in fact better than silicon.
Any further question? Yeah, Professor Büchner?
This doping, which you showed at the end, so is it possible for any perovskite? Can we provide you with a magnetic, whatever perovskite, and you dope it? Is it possible or not?
So it would be possible with two conditions. One is that the energy levels of the host, in case you're perovskite, would have to match the dopants that we have available. That's the first point. And the second point is, of course, the processing. You need to be able to process them together in the same fashion. So if that perovskite could be evaporated, then absolutely. If one would have to create a different way, then we will have to look at other dopants that are compatible with other processes. But in principle, yes. In fact, we had selected here a lead-based perovskite, which has a relatively large band gap of 1.6. It's always easier to dope materials with a smaller band gap. So in this case, we actually made it a bit difficult for ourselves by going for a large band gap perovskite.
Are there more questions? Please, there, here in the row in the middle.
Thank you, Yana. I have a question about the other end of the life cycle, the beginning of the life cycle. A lot of criticism is often about the resources that go in. For example, you mentioned the lead, but also as an alternative tin, which is also a conflict mineral. And I wondered if you compare the two solar cells, are there other advantages or disadvantages in terms of the ingredients, so to say?
It's a great question. I think still in the perovskite research, it's sort of early days. So we're looking at addressing the key challenges before we can really go into the full, production value and how to look at all the different resources. I believe personally that the instabilities that are present for tin-based perovskite will not make them competitive enough. And so I could imagine that perhaps some mixtures of tin and lead could be interesting because especially of the very low band gap. But overall, I would say the focus will still remain on lead-based perovskites. And perhaps one example for that, if you look at the European Union guidelines for electronics, so lead is forbidden in electronics, but photovoltaics is excluded from this category. And so perhaps we could imagine that there is a reason for that.
Any further questions? There.
Thank you for the fascinating talk. Have you considered the use of artificial intelligence to assist in the design and optimization of your, manufacturing process?
Exactly, absolutely. That's where we're going. We realized over the last number of years that the human factor is sometimes the most important factor. And that means that if you really want to do research on a large scale and also with many different parameters, you need to automate the fabrication of the solar cells. And once you automate, you have to involve AI in order to help you choose the next best set of parameters. So our next step would be to form a perovskite solar cell fabricating robot, and then let the robot do its job guided by artificial intelligence. And it's already been tested in, I would say, a number of laboratories. It works really well because it completely expedites and accelerates the advances that we gain, both for performance, but I would say performance is now well tackled, but especially for stability. Which critical parameters in the processing would then influence the stability of the device?
Any further questions? If not, then thank you very much for the very excellent question and answers, actually all to you, the audience, and to you, Professor Vaynzof. Then it's up to me now to come to the last official step. May I invite our rector, Professor Staudinger, Magnificency, to handle over the flowers?
Oh.
So I think it would be nice if you could do it. Yeah?
Of course.
Please. Is it okay for you?
Flowers,
Thank you so much.
So,
Wow.
celebrating your arrival.
Thank you very
at
much.
W3. Let us take a break.
And also, thank you very much from my side for welcoming to Dresden. I work already with many of you, and I hope to work with even more of you in the future. So thank you.
So you are all invited to join us at the get-together now. And then we can, of course, continue question and answers and talking to each other. Thank you very much.